developed the ideas of special relativity, the special theory of relativity. They began to think of the world as a four-dimensional world rather than... Now in a one-dimensional world is like life on a railroad track. Once somebody has, in this one-dimensional world, you have to specify one number. And, 5 miles means you're 5 miles down the track, or motion requires one number to tell you where you are. A two-dimensional world, like the surface of this drumhead here, someone's built the station house. To know where you are in a two-dimensional world, you need to know how far this way and how far that way, two numbers, so far this way, so far that way, and so much altitude, for example. But in space-time, this fourth dimension, which was proportional to time. And in this four-dimensional world, you needed four numbers to tell you where you were and one number to tell you when, so that the points in this four-dimensional world, and they had a when. Now that was all the special theory of relativity. But Einstein went on to into a more general theory called the general theory of relativity, which was a theory of gravity. Now Newton had forces on one another proportional to the mass of this one, the mass of that one, and the square of the distance between them. Because if you think about it very, very long, you begin to wonder, how does the Earth over here know that the moon, let alone that it exerts a force on the Earth? Well, Einstein provided an answer to that question. Let me use this drumhead here as an analog to the four-dimensional space-time that Einstein had to explain gravity. If you had just a lone planet, say this ball moving through space, in the absence of a sun or a star in the vicinity, would follow a straight line at constant speed to be uniform motion. Feel a very massive planet or something like a star like our sun, and if that mass is put into the planet, then no longer follows the straight line at constant speed. Rather, it follows the curvature of the space-time, and so the planet, as it moves past the star, is not reacting to the curvature of the space-time in the vicinity where it actually finds itself. Consequently, it then goes, or can. Well, that was the idea of general relativity, that the presence of mass gives curvature to that space-time. Science fiction writers have played with that idea, and black holes and so forth, that are consequences of the curvature of that space-time by very massive objects. People soon realized that there was a way to test this idea of Einstein, that space-time was curved space-time. The idea was this: light is a lump of mass energy. In special relativity, it all one thing, mass hyphen energy, and light represents mass energy. And so light ought to follow the curvature of space, the Earth. And so the idea was this: if the sun were not there, and you look in the absence of the presence of the sun, then you'd see the light come to your telescope along a straight line, and you'd say, okay, the star. But if you put the sun nearly into the path of the light, now the light follows and gives the impression that the star has actually shifted position, because the light seems to be coming by sighting back along the direction of approach of the light to their telescope. And so that experiment was done as one of the early tests, and quantitatively the prediction of general relativity was borne out by these experiments. They were done during an eclipse, and then people looked at the light arriving from a distant star to see whether it had followed a curved